Would you like to introduce yourself?
Yeah, thank you. All right, well, thank you. I'd like to introduce Derek Fowler. He started with me. He actually started volunteering in the lab last semester doing some projects, and so we got some experiments, and we were doing a lot of frog work, developmental tox work in the lab, and we were doing some work with some dyes, and I let Derek look up the dyes we had in the lab, and he found this dye, acid fusion. So he's got some preliminary experiments here he's showing you that just got hot off the presses. Some of them were Friday we got done. So anyway, thank you.
All right, good morning, everyone. I'll be doing my PowerPoint on the use of Xenopus embryos for determining the development of toxicity of acid fusion. So pterogenesis, it is basically what we're looking for in this experiment, and it helps find the toxicity levels that I'm looking for in acid fusion. And it basically, when we find it, it basically says that the performance inside the organisms and what it can cause in their certain environments. The effects of acid fusion, they're found in wastewater and basically paper, rubber, plastics, any type of production and that use. But like when they're found in the wastewater, they can cause like effects to certain organisms, and there are certain levels in oceans and river waters that you can find it, but there's no exact way of cleaning up this wastewater. There hasn't been research done to fix those problems, but further research is being done to fix that. Xenopus and VTAGs. Xenopus, they are a particular frog. They are an African frog, and in this experiment, they are reliable and seen to be reliable in research. So that's why we use them, and they've been proven throughout our articles and what we've been using. And in this experiment, the VTAGs is like basically an experiment that is a 96-hour experiment, and it's just a guideline to help us find what frogs, like what goes on with the frogs and what guidelines we have to follow to get done with the frog. Yeah. The overview of VTAGs protocol. So the day before, we inject the frogs with an HCG called human chronic gonadotropin, and it takes about 12 hours for them to be injected, and Dr. Rayburn does it on Sunday nights, and then we proceed doing the process on Monday mornings. And once the eggs have came, we use a cytosine that's about 2% with the 8.38 pH, and it basically cleans the eggs and helps us get to their Cleveland-Gastria to their early gastrula levels, which is their early lifespan cycles. Why do we use Xenopus frogs? We use them because they're easily to maintain. We don't need to feed them. We don't need a particular tank for them or just particular breeding for them. It's just easy to use. They can be bred year-round, and we can inject them with the HCG any time of the year, which is also helpful. And there is extensive literature and background for the frogs, so that we can go back and look at old information they might have on them that could help us further research towards the future. And they have transparent embryos, so any problems we may see inside the embryos, we can use to find, like, we can see their hearts, we can see their organs, we can see all types of things, so it's not hard on us to find their problems or anything that's going on with them. And once the frogs are injected, they're easily reproduced at a high level for the experiments. So we can run about 3 to 5 experiments at a time, because they produce so many eggs at a time, which is great. hypothesis is acid fusion will be teratogenic and have a potential to cause birth defects. And our objectives is to find an LC50, which is the 50% level of mortality inside the frogs, the overall frogs, and EC50 is the concentration, my highest concentration of frogs at a half level as well. NCIG is the minimum growth that I will see inside the frogs from acid fusion, and teratogenesis is what TI is. Materials and methods. In this experiment, we basically just use petri dishes, microscopes, acid fusion, Fetex water. So we put the frog embryos inside the petri dishes, and we separate them by each concentration. And the first four, as you see, are my controls, and then below those are my first concentration to my highest concentration at the end. And every 24 hours we change the dishes, and yeah. And here's another slide detailing that. Yeah. Test finish. It takes about 96 hours for the experiment. So I've said this in a couple of slides. So Monday is day 0 and Friday would be day 4. Because Monday we actually just setting up the experiment and we're just putting the eggs in each one of its stages, and it just takes 24 hours for us to finally see the results and continue the process. And the 24 hours we change the solutions, we take out any dead embryos that might be inside the petri dishes, and then we re-put new solution. And these are some of my results. So the one on the left is just a normal frog embryo tadpole, and it has nothing wrong with it. And as you see on the right, that's the one that has effects from acid fusion. And as you can see, the tail is starting to wrinkle up, and like it's starting to disintegrate basically, and the head as well. And you can see a little bit of edema in the gut. And this is my first results from my first experiment, and we didn't get exactly what we wanted in our first experiment. We got low mortality, but we got high malformation, which was great. Like, we got some results, but what we want is higher mortalities in the experiment, and about the same malformations, but we want mortality to be higher than malformations. This is the first and second experiment together, and basically mortality finally peaked. The malformations finally peaked, and malformations was the one that just stopped. And that was good for this experiment. It just shows that we finally found a certain concentration it takes to basically take out the frogs at my highest concentration. And this is just basically an example of what I was just saying. At LC50, the concentration I needed was 1120, but the concentration that was needed for the EC50 was 406. But at 1100, we didn't exactly know the numbers for that, so we used the concentration of 2000 to figure out what exactly it would take to take them out. And the TI levels, the teratogenesis levels, we needed 1.5 to prove that there was teratogenesis in this project, but we got 2.84, which is even better. So it was double the standard. And results, as you see, as I went up my concentrations from 0.1 to 1 to 10 to 100, the size of the embryos started to decrease, and that shows basically what I was explaining in my previous slides. And in conclusion, we did find LC50 and EC50 in my last experiment, which we just did Friday, and we need to run at least 2 more experiments to conclude that my hypothesis that I'm trying to find. And basically, all this is preliminary data, so we need more experiments. So I can't conclude for sure that what we are experimenting is exactly proven in my hypothesis. And I just want to acknowledge my lab partners, Critical and Shelby. They also helped me in the lab and just guide me in the right directions. They've been in the lab longer than me, and I just appreciate them for what they've done for me. Any questions?
On the picture that you showed of the embryo that had a malformation, at what concentration was that?
That was at 2,000 concentration.
And do you have any idea what concentrations are in the water? Like in the wastewater?
No ma'am, but like it's not at the highest level. It's not at the highest level that I'm looking for. We're just trying to figure out what level it would be found to exactly hurt the environment. We haven't really tested like the highest concentrations in the wastewater, but basically they have been detected in the wastewater. So we don't know the highest concentration, but we know they are having some effects on the environment.